everyone. I'm Anne. I work with Suzanne on seismology research, and over the summer, I've been exploring methods to detect small seismic events in a noisy urban environment. So for some background, I'm really interested in induced seismicity, which refers to earthquakes and tremors triggered by human activities like mining and wastewater injection. Because of this, the number of earthquakes in the central US has really skyrocketed in the past decade. And a potential case is this 2013 magnitude 3.2 earthquake that happened near a quarry in a suburb of Chicago. It's possible that quarry operations like rock extraction or dewatering may have triggered this event. So Suzanne and some students installed a seismometer there to detect additional events. But the challenge is it's extremely noisy data. It's full of urban noise events like quarry blasts that can both hide and resemble small earthquakes. So to address this, I first explored my data a little bit. This is a spectrogram which shows how noise levels change over time at different frequencies. And you can see how this column right here is a Sunday, and it's much quieter at high frequency bands than at other days when you have something like the quarry conveyor belt operating. I also saw this really cool signal over there, which is like 3 bursts in a short interval, which might be some sort of temporary construction project. But what's really interesting is that when you look at the unfiltered data at all frequencies, it doesn't look like there's much going on there. It's just a lot of random noise. But then when you filter it so that you're only looking at that pertinent frequency band, you see this clear pattern appear, but which I thought was really cool, but it's completely hidden by noise at other frequencies. So this leads me to detection methods. Mostly seismometers are placed in remote areas. So a common detection method is called STALT triggering, which moves through your time series, computes an average amplitude in the short-term window, which is shown in blue, and then average amplitude in a long-term window shown in red, and computes their ratios. And when it hits a high amplitude event like that one, then the ratio is going to spike and set the triggering algorithm off. But then when you have a noisy urban setting like this one, this is the same signal I showed you earlier with the cool hidden signal inside. You can see how it's really not helpful at all at detecting these events. And so what I've been doing so far has been implementing Python programs that implement the same methodology as STLT triggering, but instead of computing the average amplitude in the time domain, compute something like standard deviation in the frequency domain, so that even if signals are hidden in amplitude, if it substantially changes your frequency content somehow, then that parameter is better able to detect that event. So these are some parameters and methods I've explored so far. I'm still exploring, but some of the parameters in the frequency domain seem to be a little bit more promising than others at detecting a wider range of waveforms and start times than STLT triggering. But that's it. Thank you for listening. Sorry, my voice cracks a little bit. I'm a little nervous.